This is Professor Corey from the Professor's Du Bois, and this mini lecture is based on the first lecture from Chapter 14 and is titled Chemical Kinetics. Chemical kinetics is simply the study of the speed of chemical reactions, and we experience chemical reactions every day. Explosions are chemical reactions that happen very quickly, while rusting is a chemical reaction that happens very slowly. Some factors that affect the speed of a chemical reaction are listed here. In this chapter, we will examine each and be able to predict how and why they affect the rate of the reaction. Collision theory is used to understand how a chemical reaction happens based on three conditions. The reactants have to collide. The collision needs a certain amount of energy, and the reactants must be in a certain orientation for the reaction to occur. The orientation piece is similar to a football quarterback throwing a pass. If the ball strikes the receiver in the back of his helmet, a completed pass is unlikely to occur. However, if the ball is in the proximity of the receiver's hands, the odds of a completion are much higher. A specific amount of energy is also required for a chemical reaction to occur, and we call the minimum energy required activation energy. This is a different quantity for different reactions and is best explained visually. The plot shown is a potential energy diagram. Potential energy is plotted on the y-axis with reaction progress plotted on the x-axis in such a way that the reactants are represented on the left side and the products are on the right. The transition state, or activated complex, is the amount of energy that has to be achieved during a collision of reactants with correct orientation in order for a reaction to occur. Some additional information provided by the diagram is a comparison of energy between the reactants and the products. You can see here that the products are at a lower energy than the reactants. This means that energy was given off during the reaction, or we could say the reaction is exothermic. The difference in the energy between the reactants and the products is the enthalpy of the reaction, or the delta H. This image shows an exothermic reaction with some values for the delta H. Notice that the value is negative. This is consistent with an exothermic reaction, and it's calculated by taking the energy of the products minus the energy of the reactants. The activation energy is shown as well. Notice how we can represent the activation energy of the reverse reaction, which is much higher than the forward reaction. Regardless of the direction, the delta H will have the same magnitude. Only the sign will change. Increasing temperature increases the rate of a reaction. We can use collision theory to describe this. Increased temperature corresponds to faster moving reactants. Faster moving reactants will have more collisions, and they will have more energy for each collision. Think of driving in a real crowded parking lot and how many more collisions would occur if everyone started driving really, really fast. This happens in Florida in the winter when the snowbirds move there. This image shows how the orientation can result in no reaction despite having sufficient energy, kind of like the football pass. For this reaction to occur, the oxygen needs to collide directly with the carbon atom. Another image representing how a reaction needs correct orientation as well as sufficient energy for the collision to cause a reaction. Reaction rate is measured as the change in the concentration of either a reactant or a product over time. In this image, one of our reactants is blue in color, and the products are colorless, so we can measure the change in the blue intensity as time progresses. Notice the plot in the lower left. What is shown is the concentration of the dye, and you can see that it's decreasing over time. The rate of this reaction is expressed as the change in concentration over the change in time, or we could say the change in Y over change in X. There are three types of rates that we are concerned with, and they're listed here. We're going to look at each. Going back to our plot, notice that there's a curve in this plot and that the concentration decreases most rapidly at the start of the reaction. So I'm at time 0. This makes sense according to collision theory. Since there are more reactants present at the start of the reaction, it is more likely to have an effective collision that results in the formation of a product. Also notice the early part of this curve is nearly linear. Because of this, we can very accurately determine the initial rate by simply using the change in concentration divided by the change in time. The portion of the plot shown here is curved, and the best we can do using concentration over time is to calculate an average rate over that period of time. The instantaneous rate means that a rate at a given time. The way this is calculated is by drawing a tangent line from the data point on the curve and taking 2 points from the tangent line and calculating the change in concentration over the change in time. This slide shows the 3 types of rates and their calculations. Don't be thrown off by the negative sign used for the instantaneous rate. A negative rate simply means that the thing you're measuring is going away. Since we're measuring the concentration of a reactant, it will get smaller with time. This would be a good place to just kind of pause the video and try to digest this slide. There's three calculations going on here. One for the initial rate, we've got an instantaneous rate and an average rate calculation. Valuable slide. If we have a rate for an element or a compound in a balanced chemical reaction, we can then solve for the rate of appearance or disappearance of any of the other species using dimensional analysis. Your textbook may show the relationship in terms of fractions, which I find to be a little bit confusing. If it works for you, use it, but I prefer just using the mole-mole relationship from the balanced equation, and I'll show you how. So we have a sample calculation here, and we're just going to calculate the average rate, and this is of the NO. So notice the negative sign with the rate, and that's because it's going away, and we want our rate to be a positive value. So we've calculated an average rate of disappearance of a reactant NO. Since we calculated that average rate, we now want to use that to calculate the rate of disappearance of the oxygen. Using the balanced equation, we know the molar relationship between the NO and the oxygen, so we're going to use this to answer the problem. Starting with the rate, I like to label it so that I set up my mole relationship correctly. So I added the NO there, and I know that there's 1 oxygen for every 2 NO, so the rate of disappearance of oxygen will be half as fast as the rate of disappearance of the NO. Our final slide for this lecture shows a plot of the concentration of magnesium measured in milligrams when it reacts with HCl in 2 different concentrations. The 6 molar HCl consumes the magnesium much quicker than the 0.3 molar HCl. This suggests that larger concentrations of reactants will have a faster rate, and this is consistent with our collision theory as well. A good understanding of this material begins with using collision theory to explain why reactions occur slowly, quickly, or not at all. In our next lesson, we will derive a rate law that we'll be able to use to calculate the rate of a reaction when our reactant concentrations are known. Stay tuned for more mini lectures from the Professors DuBois channel.